An online reinforcement learning algorithm for episodic Markov decision processes with unknown transition functions and stochastic rewards is presented. The algorithm employs optimism in the face of uncertainty and comprises two components: model estimation and policy optimization. To address the online MDP, the algorithm utilizes occupancy measures, bridging the problem with linear programming. This connection yields a regret bound of L square root x a t, where L represents the episode length, t denotes the number of episodes, and x and a signify the cardinalities of the state space and the action space, respectively. Notably, this bound surpasses those achieved by UCRL, UCRL-2, and Regal algorithms, and matches the best-known regret bound of the UCBVI algorithm. In contrast to previous approaches, the proposed algorithm optimizes the policy through an optimistic approach in the face of uncertainty, considering both model estimation and policy optimization. This strategy mirrors the concept of optimism in decision-making over a fixed time horizon, often applied to multi-armed bandit and reinforcement learning problems. By establishing this connection to related works, the paper demonstrates the effectiveness of incorporating strategic optimism into decision-making processes, leading to improved performance in complex MDPs. Furthermore, this research highlights the potential benefits of adopting a linear programming framework to address the challenges posed by unknown transition functions and stochastic rewards in online reinforcement learning. In episodic Markov decision processes, MDPs, reinforcement learning is a crucial task. This paper proposes a novel approach that builds upon existing optimism methods and confidence set-based algorithms. By combining the upper confidence bound (UCB) approach with a Q-learning type algorithm, the authors achieve a regret bound of L square root texa, similar to previous works. They also draw inspiration from posterior sampling, or Thompson sampling, which has been shown to achieve a regret bound of L square root texa in certain settings. The author's contribution is twofold. Firstly, they improve upon the best regret bound of existing algorithms that adopt the same method based on confidence sets, reducing the bound from L 3/2 x square root ta to L x square root ta. Secondly, they improve the computational efficiency of their algorithm by reducing the number of steps for model estimation and policy update from t to at most x log t, at the cost of an additional factor of square root x in the regret bound. The paper defines key notations, including the probability simplex of a finite set A, the indicator function, and the asymptotic lower and upper bounds. The authors focus on the layered episodic MDP model, defined by a tuple M equals x, A, P, R, where x is the finite state space, A is the finite action space, P is the transition function, and R is the expected reward function. This model satisfies certain conditions, including that the state space X can be partitioned into non-intersecting layers, and that state transition takes place only between two consecutive layers. The learner interacts with the environment over a fixed finite time horizon t, following a learning algorithm to learn the optimal policy for the MDP. The learner determines a stochastic policy pi t in each episode t, which is executed over the entire episode. The learner receives bandit feedback in the form of realized rewards, and the expected reward over an episode is defined as the sum of the expected rewards received in each step. The author's algorithm and results can be applied to any general episodic MDP model, up to a scaling factor that depends on the length of each episode. In the context of episodic MDPs, the occupancy measure is a pivotal concept for learning the optimal policy. Denoted as QP, pi, it represents the probability of visiting a specific state action state triple, x, a, x, under policy pi. This measure is defined as the probability of transitioning from state x to state x, through action A, given the transition function p and policy pi. The set Q denotes all valid occupancy measures that can be induced by some arbitrary transition function p and policy pi. This set is a non-empty polytope, a geometric object with flat sides existing in multi-dimensional space. The paper also introduces the concept of QP, which represents the set of all occupancy measures associated with the transition functions in P. The authors then describe their proposed algorithm, Upper confidence reinforcement learning using linear programming, UCRL-LP, drawing inspiration from previous algorithms such as UCRL, UCRL2, OREPS, UCorEPS, and UOBREPS. The UCRL-LP algorithm consists of two primary components: maintaining confidence sets for transition and reward functions, and solving a linear program for occupancy measure update. The confidence sets are constructed using the technique of optimism in the face of uncertainty, a method widely adopted in the existing literature of online MDP and bandit problems. The UCRL-LP algorithm is a model-free reinforcement learning algorithm that leverages linear programming to efficiently compute the optimal policy. It maintains confidence sets for both the transition and reward functions, ensuring high probability that these functions lie within the sets as learning progresses. The algorithm operates in epochs of random lengths, adopting a doubling epoch schedule similar to UCRL2, UCorEPS, and UOBREPS. This technique significantly improves computational efficiency without negatively affecting performance, reducing the total number of steps for policy update to at most log t compared to general reinforcement learning algorithms which update policies after each episode. The empirical estimation of transition function p in epoch I is given by equation 10, where ni x a and ni x a x represent the number of visits to x a pair and x a x triplet at the beginning of epoch I. The confidence radius EI, x, a, is defined in equation 11, using a confidence parameter delta. The confidence set pi is defined in equation 12, including transition functions that are close enough to the empirical estimation with respect to the confidence radius. A key aspect of the UCRL-LP algorithm is the computation of the occupancy measure, which is efficiently updated by solving a linear program over the polytope QPI. This polytope has a closed-form description provided in lemma 1, which allows for efficient computation of the occupancy measure. The lemma provides a representation of QPI as a non-empty polytope, defined by a system of linear constraints, enabling the algorithm to efficiently update the occupancy measure and policy pi equals pi chi. The authors introduce two lemmas that provide high probability bounds on the rewards and confidence intervals. Specifically, lemma 2 states that with high probability, the empirical estimation of rewards in epoch I, denoted by re x a, is close to the true reward r x a. Meanwhile, lemma 3 provides upper and lower confidence bounds, re x a and re x a, respectively, that bound the true reward with high probability. The authors then describe the linear programming approach for updating the occupancy measure in each epoch. The algorithm solves a linear program, denoted by LP1, to determine an optimistic occupancy measure, chi, that maximizes the expected reward. The policy pi induced by chi is implemented for the entire epoch. The main result of the paper is presented in Theorem 4, which provides a regret bound for the UCRL-LP algorithm. The regret is decomposed into four components: biasi, diff, error, and biasii. The authors analyze each term separately, using the lemmas and linear programming results to establish bounds. In particular, biasi is shown to be non-positive with high probability, diff is bounded by 0 with high probability, and error is bounded using lemmas 4 and 5. Lemma 4 provides a bound on the accumulated difference between occupancy measures induced by the implemented policy over the actual and estimated transition functions, and lemma 5 uses this result to bound error. Finally, biasi is bounded using the confidence intervals established in lemma 3. Overall, the authors demonstrate that the UCRL-LP algorithm achieves a regret bound of O, LXT log, TXA, delta, with high probability. In episodic Markov decision processes, a novel algorithm for reinforcement learning achieves an EO, LX square root ta, regret bound while requiring at most x log t solves of a linear program for policy updates. This efficiency is attained by maintaining confidence sets and solving linear optimization on the polytope of occupancy measures, leveraging standard linear programming solvers. Notably, this approach reduces the regret bound by an extra factor of square root L compared to earlier confidence set frameworks, and improves computational complexity from O(t) to O log t, compared to alternative methods with slightly tighter regret bounds. The proposed algorithm's significance lies in its ability to balance exploration and exploitation in complex decision-making processes. By adopting an occupancy measure framework, the algorithm efficiently updates policies while minimizing regret. The authors highlight potential future research directions, including the removal of the square root x factor in the regret bound by integrating the occupancy measure framework with Q-learning-based algorithms. The paper also provides a comprehensive review of reinforcement learning and control applications in various domains, including cyber-physical systems, healthcare, and building controls. These applications underscore the importance of efficient reinforcement learning algorithms in real-world decision-making scenarios. In this section, the authors delve into the proof of lemmas 4 and 5, which are essential components in establishing the main results of their paper. They leverage techniques from prior works, 22, 23, and introduce new ideas to tackle the challenges posed by the online learning setting with bandit feedback. The first step involves defining the transition function pi and occupancy measure q, x, a, for each epoch I. The authors then utilize a series of lemmas to bound the error between the estimated and true occupancy measures, ultimately leading to the desired bounds on the cumulative error. These lemmas, including lemmas 7, 8, and 9, rely on the concentration inequalities provided by the Azuma-Hofding inequality, lemma 10, to establish the required probabilistic bounds. The proof of lemma 4 begins with the application of lemmas 7 and 8, which allows them to express the cumulative error in terms of the model estimation error xi, t, x, a. By applying the bound from lemma 2, they show that xi, t, x, a, is bounded by 2 by t, x, a, with high probability. This leads to the final bound for the cumulative error, as stated in lemma 4. The proof of lemma 5 follows directly from the bound on the cumulative error and the fact that the estimated reward function re, t, x, a, is bounded by the true reward function r, x, a, with high probability, as per lemma 3. This results in the desired bound for the cumulative error, as stated in lemma 5. In conclusion, the authors successfully leverage existing techniques and introduce novel ideas to prove the key lemmas necessary for their main results. The provided bounds on the cumulative error and the estimation error xi, t, x, a, are critical components in establishing the efficiency of their proposed algorithm for online learning in adversarial MDPs with bandit feedback. The authors continue to analyze the bias of the BIASII algorithm, focusing on the occupancy measure Q element of Q with probability at least 1 delta. The bias is bounded by two terms, as shown in equation 31. The first term is bounded using lemma 11, which states that with probability at least 1 delta, the term is less than or equal to 2L square root t log txa delta, as shown in equation 32. This is achieved by applying the Azuma-Hofding inequality, lemma 10, to a martingale difference sequence, yielding equation 33. The second term is bounded using lemma 12, which states that the term is less than or equal to 5 SDLXA log txa delta, as shown in equation 34. This is achieved by bounding the number of visits to each x, a pair in each epoch, using results from 16 in Jensen's inequality, as shown in equations 35. Combining the bounds from lemmas 11 and 12 completes the proof, providing a bound on the bias of the BIASII algorithm,